I'll just start sharing my screen. Just a second. Okay, so is my screen visible?
Yes. Yes.
Mhm. So okay, so what we want to do, so in the today's class, whatever sir has taught, would someone like to brief what he has taught in the class today? Just a small brief of whatever has been taught. So he must have taught something related to this, right? What is this? Someone says a basic overview of ASIC design. So would someone like to just mention simple steps, whatever you might have gathered from the morning's class?
We moved from idea to chip. Uh, we started from idea, then we moved to the RTL level, RTL to GDS, and then the fabrication process. Means we got to know the basics.
So first thing you told me about it is idea, right? So we are today from idea to we'll move to RTL. Okay. So this would be the first thing that we would be doing for today's lab. So basically, we'll be covering all the steps that sir teaches in the class in the morning, and this is what we want to do for today. Okay, so it is the first step. So what can an idea be? So what do you think by idea? What do I mean by an idea when I talk about real estate design flow? Hello. So what do you mean by an idea when you talk about real estate design flow?
For an instance, we want to create, uh, just for an example, we want to make a chip that would perform like the count. It will act as a counter.
Okay. So you mean to say a functionality, right?
Right. Right.
So functionality may be called an idea, correct? So right. So you have an idea. Now, what is an RTL?
Register transfer level.
So basically a hardware description of the idea. So basically how will this idea translate into digital circuit? This RTL defines that. Okay. So you give this is hardware description language, basically HDL. So there are various hardware description languages, Verilog, VHDL, system Verilog. Okay. So there can be various languages. So this HDL is what defines it in hardware. Okay. So now you are saying that let's say there was a counter. I want to make a counter. Okay. So I can define that. Okay, first this state will come, then this state will come, then this will come. Okay. So this is an idea that this is how it is. It should work. This is a 3-bit up counter. Then again here. Okay. So this is a state diagram. This is the idea that you have. But now you want to translate this idea into this HDL. Okay, so you now write you use a language called, so we'll use this Verilog to define this functionality. Okay, this functionality. So how many of you are aware of C language? Almost everybody, I suppose. So people are aware. Yes, Sudhir, do you have any question? Okay, I think you are telling about this. Okay, so C language basically you define a function. Again, there also you define a functionality, right? You have an idea, you define the functionality in C language. But what do you think is the compulsion that I cannot use C language uh, to define a digital circuit? I could have used a C language already, so there was a programming language available to me which could have done the same thing to define the functionality. Why do you think it is required to have this Verilog extra? Hello? Does someone have an idea whether you can use C language for defining digital circuits or not? Let's say you had to do A equals B plus C. Okay. This is, let's say, an half header. Half header. This could be defined in C language, right? But why do you need a Verilog language at all?
C is not a language.
Sorry, whoever is speaking, please speak loudly. Okay, so what happens in digital circuits? So there is a lot of parallelism, okay, which is not there in C, right? In C language, you do everything sequentially. I am talking about a single thread, okay, single thread. Okay, or you can do multi-threading. That is another thing. That is a different thing. But in a single thread, whatever happens is it is happening sequentially. But in Verilog, you can actually make it behave like things are happening in parallel. Okay. For example, let's take a shift register, a small shift register. This is input, this is output, this is a clock. These two are D flip flops. Okay, we have connected it like this. Okay, so if I say that this node is let me call it Q. Let's not call it Q. Q is already there. Let me call it this one. Let me call this one A, this one B, and this one C. Okay. So what? So first of all, tell me what this kind of serial. So what this kind of shift register is called as?
Serial in, serial out.
It is serial in, serial out, right? So what should happen is when you give it a clock edge, then what should happen? This data should go here, and this data should go here, right? Then what should happen is C should become equal to B, and A should become, no, sorry, and B should become equal to A, right? But let's say if you write this code in, let's say, in C language, you write this that for defining this, that at each edge of the clock, you detect the edge of clock and then say that B is equal to A, and C equal to B. Would it work as a shift register?
No, sir.
So what is the problem here? What is the issue in this definition of shift register?
So in terms of Verilog,
No, I'm writing it in C language. Even in Verilog, this won't work. But tell me what is the issue with this kind of definition of shift register?
so we are changing the value of B.
Okay, so you have changed the value of B. Then what happens? Someone is saying input will become equal to output.
Sir, both statements will execute at same time. This is the problem.
If this is C language, then this will first execute and then this will execute. This will execute first, then this. Okay, so Kanika Singh says that C will also be equal to A, right? So in the actual shift register, what should have happened is the value of B should go to C and value of A should go to B, but A should not become equal to C. So basically these two are not equivalent. But in this statement, what happens? C equals to A is also the implication. But in the Verilog language, there is a something called as non-blocking statement. Non-blocking. Okay. So in the non-blocking statement, everything happens parallelly. Okay.
But this is a blocking statement, right?
This is a blocking statement.
Yeah.
But the non-blocking statement is not available in C
Yes.
language, right?
Yes, sir.
So in the Verilog, you can put it like this.
Yes.
And then what will happen? A will become B, and at the same point of time, B will become C. So C will become B, but vice versa. B will become A, and C will become B, and then you will actually get this kind of behavior. Okay. So basically, what happens is to exploit. So basically, make it behave like parallel execution. You need some kind of language, which is Verilog. Okay. Although Verilog is also executed in form of C at the backend. Okay, in the backend it is implemented in C only, but at the level of abstraction we look at it like a Verilog, like a new language in itself. Okay, so what you need to take care while talking about Verilog, it is that you have to think hardware. Okay, think about hardware. So this is the important part. So what I will suggest is, we are not going to learn Verilog in the labs, and not even Sneh sir will cover to some extent, but it will not be so much that you will be able to uh, do everything that you want to do in Verilog uh, just out of the classes itself. Okay, so because the scope of the classes and labs is beyond Verilog. So I suggest you to learn yourself, okay? And it is not very difficult, believe me. Someone also named a website called HDL Bits. HDL Bits. We'll share the link for this website, okay? So what you can do is go there and log in, and there are simple problems there, okay? Simple problems. You just attempt those problems. You may use some Google or whatever. So whatever you want to do, just try to solve these problems, and then you'll be able to learn this Verilog language. Okay. Till then, in today's class, what we will do, we'll write a code of Verilog code. So it will be a demo for you, a Verilog code for a full adder, okay, and another Verilog code for counter, 3-bit up counter. These two codes we'll write, and we'll see that if we are able to do so, then we may move to FSM. Okay. We'll create an FSM using these two modules. Okay. Okay. So before moving to this, let's talk about the functionalities. Okay. So tell me, what is the functionality of full adder and what is the functionality of 3-bit up counter? Hello. What is the functionality of full adder? This is a simple digital circuit, combinational circuit. Hello, am I audible?
Yes, full adder is a combination circuit with three inputs and two outputs. Two inputs are like three inputs are A, B, and the C input that is carried forward from the previous addition. Output is sum and carry. Sum is A XOR B XOR C, and C out is A dot B plus B dot C plus A dot C.
Okay, thank you. So what is the functionality of this one? The 3-bit up counter? Hello? Can someone please tell?
3-bit up counter would, if considering it to be a ripple counter, would count from 0 to 7. On every clock, the new state would get triggered.
Okay, okay, thank you. So these are the two functionalities we want to achieve. Okay. So let's move to writing the code. Okay. Uh, okay. Uh, One more thing. Let me explain one more thing. So in these labs, right? So we are going to give you demo for RTL to GDS. Right? We'll write an RTL. We'll take it till the GDS. Okay. So what you need to learn, okay, what you need to do is you follow the labs, okay, relate it with the theory, okay, try to relate it with theory, ask doubts in the lab, and keep documenting, okay. Once you do the so basically whatever examples we are doing in the lab, if when you do it on your own, then you just document it, you take screenshots and make a PDF, okay. uh, Try to create a PDF. So what we will do is at the end of the course, the uh, labs activity, whatever we are doing, that will become your final project. Okay, the compiled form of this lab will become your final project. You will be submitting a report. Okay, so there will be a report that you need to submit at the end of the week. So this makes everyone's job easy. We'll just have to teach this flow complete RTL to GDS, and you have to follow, and by following you'll be able to complete the assignment and also complete the labs activity. And believe me, if you are able to do all this, then you will have a complete project at the end. Okay, so you will be able to put this project in your CV, and it makes a lot of impact. Okay, you are doing everything with Cadence tools, so in any interview or wherever you go, it will create a lot of impact on your CV. Okay. So this is out of our experience that whenever we sit for interviews, these kind of projects are actually something that attracts the other person. Okay. So I advise you to do it continuously. Do not let it for the weekend. So do not do it just on the weekend. Do the labs as they are given. Okay. Whatever we do in the lab, we just do that at your own place. Okay. Okay. So now I will start. So you guys were not given the iVerilog tutorial, right? Okay, let's straight away start with the mobile stuff. Okay, so for the ones who have not been in this course for the last few weeks, okay, so you might not know how to log into mobile system. So can you please raise your hands if you are not able to log into mobile system? How many people are not able to log into mobile system? Okay, there are people. So I'll first demonstrate that only. Dave is not. Okay, sure. So what you need to do is, so basically you have this session button here. Okay, this session button. Okay, then you go to this SSH, and then you go to this remote host. Okay, inside this remote host, whatever your IP address that has been provided by IT help desk of triple IT Delhi, that you put it here. I think this is that would be 103.1 whatever. So it would be something like this, and then you put your username here. Okay, specify your username. For example, my username is Gagandeep2032. Okay, yours will be different. That will be shared by the IT help desk. Now, once you do this, then you will be asked for your password. Okay, let me first put my remote host ID. Okay, mine is okay. I will this one. So 192.168.3.32. Okay. Now I'll specify my username. Then I will do okay. So after this, it will ask you for password. It has not asked me for password because I have saved my password already. So then you will be able to log in after putting your password. When you put your password, you will not see anything on your screen. For example, I am typing something. I am seeing that whatever I am typing is coming on the screen right now. But it will not happen when you enter the password. Okay, so do not worry if you are not able to see the password, but just enter the correct words and alphabets and go ahead. Okay. So other ways you write SSH -x your username and then the IP address. Okay. So this is another way of doing the same thing. Okay. So I prefer this one, but I showed you the simple way. Okay. This is the simple way that you do. Go to session, go to SSH, go to remote host, specify the username, enter the password, and start working. Okay. Okay. So I think. Whosoever may have not attended the previous classes, you can look at the recordings later. So let's start. I will first make a directory for this course work. Okay. Mkdir. So this is a Linux command for making a directory. So my directory name will be vdf vlsi. Okay. So I'll go to change directory. I'll go into this directory. Okay. Going cd vlsi revisited, and slash means I'm going inside this directory. Okay, whatever is the front slash is indicator of the next directory, searching for the next directory. Okay, so now I will start this gedit. So gedit is basically a way to open editor. Okay, so I will first write a counter. So do you know what is the extension of a Verilog file? A file in which
Dot V.
Dot V.
okay, so I'll write counter dot v. So a window will open up. Although I prefer to do it over here. So basically, what I will suggest is you write in Visual Studio. So basically, this is Visual Studio, right? So most of you will be aware Visual Studio code. So what you should do is you write inside this Visual Studio Code and then copy paste it here. But I think I am avoiding to avoid to make things complicated. So I want to just write it here. Okay. Although that is a better way. So that is what I like. But we'll go this way. Okay. Okay. So counter. Uh, so first of all, what happens is in Verilog language. First of all, you define a module. Okay. So any design is called as a module. Okay. Any block that you want to make is a module, and this is the way you comment. Okay. So I have commented. So this is the same way you do it in the C language, the comment. So I will define a module. So this is a module, and then I will. So basically, this is a directive that I'm. This is a declaration that I am going to define a module. Now, while defining the module, I will say counter. The counter is the name of my module. Okay, and then what I will do is I will put two brackets and then put a terminator. This is the syntax. Okay, this is nothing. This is syntax. Put a terminator and then enter and end module. This is how you define a module. Okay, so I think there is no scope of any confusion here. Uh, Now I have defined a module. So what should be the inputs of a counter? Tell me. And inputs and output of a counter. I need to define the input ports and output ports of this counter.
Sir, clock.
Clock. Okay. Anything else? The output? What
Reg.
Sorry.
So reg.
What would be the reg?
Reg for input and for output.
Why do you want to put a reg? What is a
So
reg?
to store the value.
Yes, you are right in saying that you store a value, but can wires not work here? Can't you work with wires?
So if we are using behavior modeling, then why won't work?
We'll see what nets are, what reg are.
Okay.
It's good that you are aware of these things. Okay, so first of all, I'll define just the input and output. Okay, so one input I'll take it as uh, that is the issue. It does not work very well. Input clock. Okay, another input. I will take a reset. Output. I will take a 2 down 0. Okay, 2 down 0. It will be out. Someone said you need a register. We'll see why do we need a register. You are correct in saying that. Let's see why do we need a register. So this output is a reg type. So there are two data types, basically two types, not data type, two types of wires basically. Okay, one is reg, another is net. Another is wire. Okay, so reg is what can store the basically store the value. Okay, it needs to be it does not need to be driven constantly, and wire needs to be driven constantly. So actually what happens is in the counter, while you increment the value, you have to remember the previous value, right? If you are increment for a positive edge of clock, when output will become output plus 1, then you need to know that what was the previous value, right? So there has to be a memory in the output variable. Okay, this is why. Okay. So now let's basically define the functionality. So I have a clock, I have a reset, I have a out. Okay. So what I write is always at the rate positive edge edge PLK. RST. If reset is high, then what I do is if reset is high, then I do out equal to 0. Out equal to three tick binary 000. Okay. So because output is 3-bit, 2 down 0. Okay. And else begin and end work like brackets. Okay. What you do, what you call as a bracket in C, here you call it as begin end. Okay. Otherwise, out will become equals to out plus 1. Let's put a non-blocking. In sequential circuits, we put non-blocking, although it is not required here. Let's put non-blocking. Okay. So this is how you define the functionality of a counter. So would someone like to explain this? I'm going to explain this. Don't worry. But would someone like to explain what this module does?
So can I try?
Yes, please.
So it means that like for the positive edge of the clock, in the begin, when we write begin, and after that we write the first conditional statement if reset, then we initialize 0 in the register. If it is not, then we increment the value to 1.
Okay. Okay. So everyone agrees with this this explanation, right?
Yes.
Yes, sir.
Okay. Correct. So this is how. So one more thing. This kind of thing in the beginning you should not do this. Okay. You just write it simply. Otherwise, I could have written it just like that. RST. Okay. That is one thing. And there is another thing that you defined that is called time scale. Time scale. 1 nanosecond by 1 picosecond. So basically, what happens is when you do simulation, okay, then you need a timing sense, right? So your timing unit becomes, so I defined my timing unit as 1 nanosecond and timing precision as one picosecond, which means whatever time I mention in this block is going to be in terms of 1 nanosecond, and whatever the precision will be, that will be 1 picosecond. Okay, whatever the smallest change in. So although I have not put anything here, okay, I could have done something like this. For example, I could have put a delay of 5, although this is not synthesizable, but I could put, this means a delay of 5 units, which means a delay of 5 nanoseconds. Okay, so this kind of thing could also be done. So once you go through the HDL bits website to write small codes, I will just give you a small demo of HDL bits if you have enough time. Also, then then we'll move on. Okay, then we'll basically, yes, Archit, please.
Sir, like if we write tick time scale 10 nanoseconds by 1 picosecond, what does this mean?
So if you write 10 nanosecond by 1 picosecond, uh, sorry. Huh. So if I write this now, then the unit of time becomes 10 nanosecond. Okay. So if I mention #5 here, so this #5 will mean 50 nanosecond. #5 means delay. So basically it adds a delay of 5 time units. Okay.
So the unit gets multiplied by the factor what we write above.
Correct.
Right?
Correct. So
Okay.
whatever timing you write, that gets multiplied with the unit of the time.
And sir,
Okay.
what about precision?
Okay, so precision is the so while in the simulation, what the smallest time change. So basically, the difference between timing that you will be able to observe will be 1 picosecond. For example, you will be able to look at the signal 1 picosecond after you observed it at the first point. right? If you note that the signal value is 1, then you'll at 1 nanosecond, then you'll look at it at 1 nanosecond plus 1 picosecond, that what is the value of the signal next. So
Okay.
this is what the precision means.
Thank you.
Okay. So I think this is pretty much simple thing. Okay. And what do you think this means? Hello. Yes. So this is 3-bit binary 000. Okay. So I'm just putting this value inside this. Okay. So now this is a counter. So this has to run 3-bit binary number. Correct. Correct. Okay. So now to run this counter, to actually simulate, to see it working like a counter, to look at the waveforms and all those things, I need to create a test bench. Okay. I need to test bench. So does someone know how to create a test bench? What is a test bench, first of all?
So file which will be used for using in the simulator.
Okay. You said environment, right? Environment.
Yeah. Environment is all for the simulator.
Correct. So the correct term is environment. It is creating an environment. So let me just explain quickly. If you have this counter, this is a counter. This is a black box. Okay, it's a black box. You do not know what is happening inside. This is a counter. You can give it a clock. You can give it a reset, and receive an output of 3-bit, 2 down to 0, bit 2, bit 1, bit 0. Okay. Now, when you want to check whether it is working fine, or when you want to look at it, like whether the functionality is achieved or not, then you need to create an environment which will actually provide. This is a test bench. This test bench will actually provide the clock from outside. Okay, and this will provide the reset from outside, and you will take the output and observe it. Okay, observation will also happen. So there is someone who is trying to check this counter. So this is a designed under test DUT, and this is the test bench. Okay. So any doubt here? What is a test bench? What does a test bench do?
So the clock reset and the output are provided externally by the test bench, right?
Yes. So test bench will be exciting your DUT. It will be giving inputs to the DUT.
So is it kind of like a stimuli what we did in cadence?
Correct. So that is the word that we use. It is giving stimuli here. Okay. So everyone has understood, or if there is any doubt, you can please ask. Test bench. Okay, that's great. Everyone has understood. Okay. So let's move ahead. So we'll create this test bench. Again, this test bench is also going to be in Verilog language. Okay. So this will be a separate file. Okay. I will again now go to my terminal and first close this. Okay. I'll close it. See, I have written it like this only. It might happen. It has some errors or whatever. We'll check it. If it has some errors, we'll fix it and then work it. Okay. So it's not that it would be error free, but let's uh, let's not complicate things. Okay. Now I will create another file counter tb underscore tb dot v. So this is how I am naming. This is how I name it. Okay. So generally people name it like this. So that is how I name it. Okay. So this file is empty. First of all, I need to give a timescale. Timescale 1 nanosecond by 1 picosecond. Then counter module. Again, you define a module called counter test bench. Okay. Now this is a test bench. Okay. Test bench does not have any input or output. Okay. It has internal signals which it generates. So again, so this diagram that I have made is a sort of incorrect diagram. Okay. Why? Because the test bench is not outside the DUT. Okay. The test bench is the DUT is inside the test bench itself. Okay. So this complete environment is test bench, and this test bench is applying the stimuli and getting the output and observing. Okay. You will see how this is happening. Now I define this module. Okay. So is that module definition complete, or I need to add a line or whatever? Do I need to do something more for module definition? Sorry.
End module.
So this is the way you this is simple syntax. Okay. Okay. Now I want a clock. Okay. Now first let's understand what is a reg and what is a net. Okay. There are two data types in Verilog. One is reg, other is net. Okay. So net is like a wire. So basically you do not write net, you write wire only. So it is a wire. Whatever value you store on the register reg, it basically remembers it. Okay. But it does not remember. The wire does not remember what was written. Okay. For example, uh, let's say there is this push button. Okay. When you press it, it comes back. Till the time you have pressed it, it will know that what the signal is. Let's say when you press it, it becomes 1. When you release your hand, it becomes a 0. Okay. So this is a net type behavior, net. Okay. Till the time you are enforcing a input, you are getting to know the input. But let's say there is a button, whatever the button that turns on your fan. Okay, so when you go into a room, when you switch on a light, what do? You just keep pressing the button and basically you keep pressing the button and light is turned on, or you just push the button and then enter the room and light always basically remains turned on. What happens in a room?
Remains turned on.
So it remains lit up. Na? So that is a register type behavior. So once you put a data that okay, you turn on, you set a signal 1, set it 1. So it will remain 1 until you make it a 0. So there is a memory. So this is a reg type behavior. Okay. So this is abstract level explanation. More you will be able to gather when you go to HDL bits or online sources. Okay. So this is a basic behavior. So reg remembers okay, the previous value. The net does not remember the previous value. Okay. So and for the same reason, net has to be okay. You have to use a assign statement, which is a continuous driving. For example, if this is a net, okay, so you want to drive it constantly. Okay, it should not be undriven at any point in time. Otherwise, it will be floating, right? You don't want floating nets in your design. Talking about ASIC, okay, at circuit level, there might be some nets that are floating. And this register, you need not put this continuous assignment. It can be done in procedural assignment. Okay, procedural is event based. For example, what you can do, you can say whenever the positive edge of clock comes, you assign it a 0, or let's say you basically do a inversion. So you can say that, okay, for some time you just forget what the value is. Okay, so basically you put a value on the register and then do whatever you want to do, and then again come and change the value. So basically it is like a switch, right? A switch that is in your room, that you use for turning on the fan and turning on the lights. You just turn on the light, you forget whatever the status of the that it will actually remember. You go back, and while going out of the room, you just again press the button, and it basically remembers that, okay, yeah, I have been turned off. So this is the basic explanation. So why did I explain this? I want to create a clock here. Okay. So that this clock will be a registered type, reg type. Okay. Why this will be a reg type? It is because I want to change the value of clock after some time. Okay. Basically, after 5 nanosecond, I will toggle it. Toggle it means I will turn 0 into 1, 1 into 0, invert it. Okay. So this is how I write a clock here. CL always. This always means that this will always keep keep going. This loop, or whatever you call it. This block will always keep going. It will be executed again and again during the simulation time. Okay. Always CLK. Okay, equals to the keyboard is not responding. So CLK is equal to not CLK. Okay. So this is the sign of bitwise not. So this is called tilde. I think on the keyboard you'll find it below the escape button. Okay, below the escape button, this this will be there. In at least in my keyboard, it is here. Okay. You may want to look for other options if you are it's not there. Okay. Now this always is here. So do you think should it work? Does it look
No,
like a
sir.
clock?
No, sir.
Why? Why? What is the
So
problem?
we have not defined the input output.
Yes, that is there. I have not defined input output. That also test bench also does not have any input output. But just tell me the clock. Just I'm talking about the clock now. Uh, would this clock work or not?
No, actually, we must give a
Delay
time.
must be there. Delay must be there in clock.
Okay, so there must be a delay. Okay, why do you need a delay?
Then simulator knows when to change, when to toggle.
Right. So there is a time instant at which you want it to toggle, right? So I'll say #5. Now tell me what #5 means.
Delay of 5 seconds.
5 nanosecond,
Yeah, 5
5 nanoseconds.
5 nanoseconds.
So this is the time unit, nanosecond, and 5 means 5 nanosecond. After each 5 nanosecond, your clock will toggle. So what is the time period of the clock?
Sir, 10.
10 nanosecond.
10
10
nanosecond.
nanosecond.
It is a 10 nanosecond is the time period of the clock. Now I have defined the clock. Now what I want to do is I want to connect the signals to the actual counter. Okay. Now in the counter, what all were things. So now let me tell you, there is something called as instantiation. Instantiation. Okay, like pretty much like when you call a function in the C or C++, you mention the name of the function and mention the parameters. Okay, here also something of that sort happens. Not exactly similar to that, but what happens is you you create copies. For example, the counter that I created, counter which had a definition like this: CLK RST output bus of 3 bit. This was the counter that I created. But when I want to test it or use it anywhere, I need to copy this, copy and paste it here. Okay, I make a copy and paste it here. Let's say I wanted to put this output inside a AND gate or whatever. I'm just saying whatever. So it does not mean anything. 3 bits I put it like this. So I copy this counter. So basically I instantiate. This is called instantiation. You create an instance of this counter. Let's say the count 0 is the name of instance. Okay, this is the definition. This is the instantiation. You can put inputs here and outputs will come out. So you define a module and then you instantiate a module. Okay, I need to instantiate a module inside the test bench. Okay, so how will I do? I will write counter. This is the name of the module that I created just now, and let's say the name of the instance is is 0, count 0. Okay, it is pretty much like human being is a abstract word. Okay, and you are an instantiation of human being. Okay, I am an instantiation of human being. Human being in itself is an abstract definition. It has some characteristics. For example, human being has two hands, it has two legs, it has one face, it has two eyes. All these things are characteristics for it. So what will happen when you instantiate a human being? It will have two legs. So the definition will be copied to the actual person. So this is the actual person that I am creating, and this is the definition of the counter that I created just now before starting to write this code. Okay, so then I want to connect these, right? So first of all, let's create the inputs, right? So the reg, right? So first of all, test bench does not have any input. You just create wires. So I'll take a wire and give it a name. Uh, so output will be a wire. Now tell me, I took the clock as a register and I'm taking the output as a wire, and I will again take the reset as register. Can someone just tell me the reason why I'm taking the inputs that I'm going to give to the module as register, and I'm taking the output as a wire? What is the concept here?
Actually, we will be making changes to the inputs to get different outputs, and at the end output would be constant. So giving it a wire would work.
Output can change, right? That is what you want to say. Output can change, and that change I want to see in the wire. I don't want to remember the previous value of output. Whatever output is coming now, I want to see that output, right? So that is why I use a wire. And input, I am going to change. For example, I assign a 0 to reset. I don't want to keep assigning it, driving it, right? I just store a 0 there, and then I'll observe that what is happening. I want to give it a 1 and then observe whatever is happening. So that is why you give input. The wires, these inputs that are going to that one in the test bench as registers. Okay. So this is an elaborate concept. So I do not basically I'm not aiming to explain this complete thing today, but okay, it's fine. We can discuss. We can give it some time. Okay? I would suggest you go and do some exercise over Verilog on HDL bits. Okay, it will help you a lot. Okay. Now to connect this CLK, this is how you do it. Dot CLK. I connect the clock of the test bench to the clock of the design. Then you write the port name RST. This is the port name of the actual design, actual module counter. Okay, and then you connect it to the local reset. Then you do this dot out and this Okay, this is how you instantiate. This is the instantiation. Now I have what I have done. I have taken a counter count 0 and connected it to the local signals that I have created just now. These are the two local signals here. Now what I want to do is I basically want to observe something. So what we'll do, clock is always running. Okay. And there is something called as initial. So in initial block, initial block starts from the simulation time 0 and runs till you let it run. Okay. So initial, begin, end. So what we want to do is during the simulation time initially, I will put clock equal to 0 and I will put reset reset equal to 1. Okay. So when reset will be equal to 1, the output will be 0, right? So what I will do after some time, after let's say 100 nanosecond, I will put reset equal to 0. Okay. And then try to observe the output for another 100 nanosecond and then finish the simulation. This directive is used to finish the simulation. Could someone explain me? I've just explained it while writing. When can someone please explain this initial block?
So in initial block, we assigned the clock 0 and reset 1 initially. And then after 100 nanoseconds, and like till 100 nanoseconds, the reset will be at 0. And then next 100 nanosecond, we observe the output, and then we finish.
Okay. Right. So please tell me if there is any doubt here. Obviously, it will not be 100% clear, but the people who are not even having an idea of what is happening here, please raise your hands.
So what is the dollar sign here of initially before finish?
So this is a directive. This is a way you write this directive. This is the syntax of writing finish. Okay. This is a compiler directive. It tells it that
Is there
now,
any command? Is there any other command that you use dollar symbol?
yes, there is a dollar time. This is
Dollar monitor, dollar strobe.
Dollar display, dollar
Yeah.
monitor.
Okay.
These all are system directives. Right. So this is the code that I have written. Now I have written this. We'll try to run this. Okay. I think in today's class we'll be able to cover the counter only. Okay. But now since I have slowly explained the Verilog or whatever, so obviously it was not a exhaustive explanation, but uh, we'll expect that you go back and do some practice and then come back and you'll be able to understand more in the tomorrow's class. Okay. So the aim is that in today's class at least you are introduced to this Verilog. Although the aim was something different, I wanted to do a simulation for FSM, but it is fine. We'll do it tomorrow and then we'll move to synthesis. Okay, it's fine. Okay, so let's move to the actual tool that we have over the server. So that tool is a quite a difficult task to run, but we'll do it. Okay, so now to invoke any tool from Cadence on the server that has been provided to you, you just write tcsh, okay, and then you write source, tcsh source slash cadence dot cshrc. Then has been kind of instantiating the counter. You just not create an error as blocking statements are used. Okay, so Kanika, a nice observation. this will absolutely be erroneous if I have done that. Okay. So, but the reason is not that it is blocking or non-blocking. Reason is that you cannot use a variable before defining it. Okay. So correct, you are correct in saying that, but I'll change it. Okay, I'll change it once I start. Rather, let's change it right now. I'll change it right now. Okay, so do not think what I am doing. So basically, this is another way of editing files. Vim. Okay, so there are various ways you can do one of them. It is easier to do it here. Okay, I'm just changing based upon the observation. Okay, Kanika, what did you want to say? This clock has been defined earlier. Or I think this should work. Hello. Okay, it's fine. It's fine. But good observation that you cannot define this clock and reset after you instantiate. Okay. So had I done that, then it will create an error. Okay. So we don't want that. So the tool which we are going to use is from Cadence, and it is NC Sim. For the simulation, I will use NC Sim. Okay, NC Sim. This is the tool name. And how you launch this? NC Launch. Okay, you write NC Launch, and then you write new dash new. Then a window will appear. Now you select multiple step. Is my computer arrow visible?
Yes,
The
sir.
arrow.
Yes, yes.
Okay, then it's fine. Okay, you go to create cds.lib and do save. Don't include any libraries. Okay. Then do okay. So now the tool has opened. Now this is the code that we have created. So let's look at it. I click at this option, edit. Okay. This is the code that we created. It is in. I have input clock, input reset, output register, and at the each positive edge of clock, if the reset is equal to 0, then you do this. Otherwise, you do this, and things should work. Okay. And then this test bench. Let's have a look at it again. So this is output. Okay. Count. This is the instantiation, right? I have basically done a clock here, initial, begin, and dollar finish. Okay. Okay. So I'll first press Control on my keyboard and then select both of them. Okay. Once both of them are selected, the both files, these files, I will go to this. Okay. Launch Verilog compiler with current selection. So do this.
So I've opened the software. It is saying like multi-step, single-step, iron, help, and result. So which option should I click?
Sorry, can you please be a little louder?
So I have opened NC launch. It is saying multi-step, single-step, iron only.
Okay, so
Which
I told
option?
you na multi steps.
Okay.
So basically, there is some problem with this compiler. Basically, what I do is I use iVerilog usually, but fine. So it is saying there is some error here, but binary should work. It should work actually. So let's not do this. Okay, I'll just put a zero, a decimal zero. It will work. Now I will again do this step. somewhere it is expecting a semicolon. You look at these logs, you will get to know the errors. Okay, so I'm just debugging it right now. Small errors will peak here and
Sir,
there, here
in
and
test,
there.
dollar finish is ended must ended with semicolon.
Correct. So that is syntax. Okay. So here we have
Sir,
not missed anything.
sir, in test bench, dollar finish is end with must end with semicolon.
So let me slow. Basically, you have to bear with the server. Okay. This is the case with almost all the tools. But if you want to learn, you need to have a little bit of time. I think. So it says that in the 17th line, it was expecting a semicolon. So I forgot to put a semicolon. Now again, we'll do this. Now it works fine. Okay. Now once you have done this, you go to this work lib and then click on the counter test bench and then click here. Launch elaborator with current selection. Now elaboration has been done. Expand the snapshots. Go here, click on this, then launch simulator with current selection. So the screen will appear a little slowly. You have to wait. Okay, so it has appeared. Now cancel this window. Don't need this. And click on the counter TV. This, and then click here. Send selected objects to target waveform window. Hopefully it should run. Okay. So I ran it from this button. Okay. So what happens is after 200,000 picoseconds, which means 200 nanoseconds, the simulation has stopped. And I will just scroll it and look at the output. So output is not as we have expected. Something different. What is happening here is basically initially, so clock is, so first of all let me show you the clock is running. Okay, clock is changing after each. So this is 5,000 picosecond. After another 5 nanosecond the clock turns down, then it comes up, goes down, comes up, goes down. Okay, this clock had to be fed inside the counter. Okay, this reset, initially it is 1. Okay, then after 100 nanosecond it goes to 0. Okay, afterwards the counter had to start but it does not start. Okay. We'll see what happens. Okay. So let's look at the code again. So I could have edited it from there only. It's fine. So if reset is equal to 0, so where is the mistake? Tell me.
Reset should happen at reset equals to 1. So
Right.
we are doing it equals to 0.
Okay, so this was a mistake. Okay. So now I will again go to the same steps and quickly do the steps now. I will not take much time. tell me, does it look fine now, or is there an issue here? See what is happening. Initially, when reset was equal to 0, at the positive edge of clock, the output goes equal to 0. Before that, it is in unknown state, which is called X. Okay, this state is undefined because there was no initial value put to the put for this one. Okay, so now tell me, what is this reset called? Is this a synchronous reset or asynchronous reset?
Sir, this is synchronous reset because it is written inside the after the always clock block.
Had you not known that where forget the Verilog code. Look at the waveform and tell me, why is it asynchronous or why is it asynchronous?
Reset triggers at the process of clock.
Okay, so that is the reason. Okay, so you will not know the Verilog code always. You have to see what is happening. So although the reset was 1 earlier, but output was not set to 0. Okay, so now what happened at the positive edge of clock, the reset did affect the circuit. Okay, now it went to 0. So let me just rather than showing this decimal values, let me show you the other value. I think it should come here. Simulation, scheduling, full time watch window, color review. I don't know. Okay, so I'll just expand this. Okay, so this is 000 here. Then it remains 000. The output remains 000. When you turn this down, okay, so at this edge, okay, this edge, output increases to 1. Okay, and this becomes 001. Then here it becomes 010, 011. It goes on. Okay, it goes on, and after 7 it comes back to 0. Why does it come back to 0? I did not give any instruction. I did not give any reset. Why did it come back to 0?
I think time 100 nanosecond after 100 nanosecond it will come back to 0.
So why does it come back to 0? I did not reset it.
Overflow occurs.
Okay. So the overflow occurs when you basically add 1 to 111, basically 111. When you add a 1 to 111, it becomes 1000. Okay, and this 1000 cannot be stored inside a 3-bit value, right? I have just 3 bits for output, so 1 will overflow. It will be discarded, and 0 will come. Okay, so you keep revolving around these eight states. Okay, so this was the demo for a counter. It was a very slow demo. It should not have taken 1.5 hours, but it is fine because many people are not actually aware of what this basically what we are doing. It is very long, so I think it is fine to cover it in this much time. Okay, uh, okay. So please ask any doubts, please, if you have any doubts. Okay, no doubts. Great. There should be doubts. Okay, you must have some doubts tomorrow. Just to get the students.
Can you please explain why we chose wires as the output? I still didn't get that explanation. Hello?
Correct. So send me a mail. Tell me that you are not having the access. I'll check it on my end whether you have the access or not. I think you asked me over the mail. I checked it. We make a project in the labs. Yes, Kanika. So whatever we are doing in the lab will essentially become a project at the end. Okay. If you follow these labs well, you have a project. You can put it on your CV, but obviously it will be basically it will be simple, but it will be for understanding it. You need to put a good amount of effort. Okay. Today's class was not very difficult. Okay? You can do it by your own. Okay. So now I will like to also introduce you to a full adder circuit. Okay. Now, since you have already looked at this counter, so it should not be very difficult for you to understand a full adder. I have a code already. Okay, I have a code. I'd rather say you please explain this code to me. Uh, Actually, there is not much that, yeah, but fine. This is what I was planning for today, but I'm just showing it to you. So tell me what do you think? How does this counter work? Sorry, this full adder work. Can someone explain it to me? Hello? Now you should be able to explain, right? You have seen a counter, complete counter, a test bench also.
What you have asked, sir? Can you ask?
I have asked,
Can you
please explain this module.
Yes, sir. I can explain.
Please do it.
This is module. Actually, you have written input A, input B, and C carry on, and output output C carry out. And you have assigned the value. You have written the formula as a assign out A jor, B jor, C jor, and written C out equal to A and B. The formula of carry. And this is the full adder in very low code.
Okay. So basically, it is a very simple code. Okay. So what I want to do in the next class, it is that I want to have a control signal. Okay. A control signal, basically, it will control a control signal C, based upon which the output of the FSM should behave like either a full adder or a counter. Okay. One of them. Okay. So that is why what I want to do in the next class. Today we will not do that. Today I have just introduced the Verilog. Okay. Okay. So should we more or should we leave today? Okay, so let's not do anything more than this today. Okay. Okay, so the full adder I will not explain this. Okay. Just look at the code by your own and try to understand, try to make sense out of it. Okay. It is a very simple code. And if you go back and try to learn Verilog, you'll know that why I'm using assign statement here and why I was using an always statement in the other part. Okay. So I will suggest that you look at this code, you understand today's lab, perform today's lab, whatever we have done in today's lab, that you do. In the next class, we will make an FSM. Okay. After making that FSM work, basically, we'll move on and do synthesis. Okay. Uh, because today I think Sneh sir has not covered the simulation part, right? He has given a general overview of the complete ASIC design flow. So from tomorrow he'll start with simulations. We'll also start with simulation from tomorrow and go with the classes. Okay, as the classes go, we'll go with the classes and we'll be able to complete the project. Okay. Before leaving today, basically more the rather most important part of today's class, I'll explain it to you how to use HDL bits. Okay, I suggest you do at least 10 questions of HDL bits before coming to the next class. You'll be able to learn very well. Okay, let me first close it. Close it. In the meanwhile, you can ask any doubt or share any feedback if you have. Was you
Sir,
able to
actually, there is a
understand today?
doubt regarding today's quiz that you have given on the classroom. The questions that are there have multiple correct options. So, should we treat it as multiple correct?
Multiple correct. Okay.
Yes, sir.
Let me check if there are multiple correct answers because
So all the questions are multi-choice, multi-correct.
Okay, multiple correct.
Yes, sir.
Let me just fix it.
And the marks allotted to each question is only 1 point. So, like, how do we treat those questions?
No, it should not be like that. It should be okay. So you reload it. Okay, reload it. I think you should
Because
have.
we haven't completed the, so okay, you can just edit it so that we can do it.
So I'm editing the form right now.
Okay.
You can complete it afterwards. Thanks for flagging this up. This is only one option is correct. Okay. Okay. So from my end, I have done that. Okay. If someone can check on their own, you can reload the quiz and you'll be able to see. Okay. So in the meanwhile, let me just show you how to log into HDL books and how to solve questions. So this is the website of HDL books. I'll share it on the classroom. Okay. You go here. Okay. And then go to this browse the problem set. Okay. You can make ID or you can start without logging in. You can make ID, whatever works for you. It is fine. Okay. You go here, getting started. Okay. Whatever it tells you. You read the question here. Okay. This question will come. This will be a question. You read the question and then finally write a code here and then compile it. If you are able to do, uh, let's say these many questions at least, then it will you'll have an idea of what is happening. Okay, then so you can do as many questions as you like. Okay, from this one, but my suggestion would be you do different questions. For example, you do this one. Okay, four of these questions, four of these questions, four of these questions, maybe not these, and these questions. So it will sort of give you an idea of very long. Okay. What I am thinking is I should put some questions on the classroom if you want. I can put some number of questions that you should do to have a good practice of Verilog before the next class. Okay, so that I can do. Okay, I'll do that. I'll do that. So basically, I'll share this website. I'll share which questions you should do. I'll suggest some questions that you should do on priority. You can do all the questions, that is fine, but it is not possible in one day. But on priority, you can do like 30 to 40 to 50. So when we started, we used to do 40 to 50 questions per day. Okay, so it is not impossible. Okay. You can do that, but let's not push it too much. Okay. So this is what I suggest. Now in the next class we'll do a simulation for FSM, and I've told you this how to do the simulation. It is so basically I suggest that you do whatever is done in the lab by today only. Okay, if you do on the daily basis, then at the end of the 5 days you will have an evaluation which will simply be a compilation of whatever you have done throughout the week. Okay, so you'll get good marks. You'll get a recognition for best student award or whatever that is going to be awarded, and also you will have a project to put it on your CV. Okay. Okay. So is there any feedback or is there any questions regarding today's session? Uh, was it basically going above the head, or was there something that you were able to understand from today's session?
So I have a question.
Yes, Archit, please be a bit
So,
loud.
so it's like for ASIC and all. So is like Verilog like very important because like most of the is RTL coding is done in Verilog and then System C.
Right. So Verilog is quite important. Okay. So when you talk about hardware description languages and you're talking about ASIC design flow, So you have to define the functionality in one of the languages. Okay, you learn VHDL or Verilog, whatever. So synthesis is done with the Verilog in India at least, and US at least, and in Japan and other few other countries they use VHDL more. Okay. I think Sneh sir would tell you that in which countries they use VHDL more, but Verilog is quite important. Okay, for
So it's
digital.
just that for some of the parts, like in when we are implementing via behavioral modeling, some of the parameter gets little bit difficult to understand.
Mhm. No, it's
So
fine.
so that
With
can only
time,
be avoided via practice, I think.
right. With time, with practice, you'll be able to understand. It will be
Okay.
a very easy task for you. Basically, Verilog is not a very difficult language, but to get into basically a mood of writing this language is a quite different, because you're not defining a procedure here. You're defining a hardware. Right?
Yes.
And that hardware mindset should be there. Then only one would be
So
able.
like the looping functionality is also a bit different in Verilog.
Yes. So here the looping is completely different.
Yeah, we cannot use I plus plus. We have to write I equal to I plus.
Even the loop has basically
Yeah,
the
begin and
significance of
end.
loop is very different here. Okay.
Yeah.
Because the hardware has to be defined.
Okay.
It's fine. You learn. So basically, in this course, at least, it the aim is not to make you learn very well. Okay, someone
Okay.
else can write the Verilog for you. You just have to work with this Verilog to arrive at that final circuit, okay, final layout. That is the aim. Remember, you the aim is not Verilog. Verilog is one part of the course. Okay, but you can learn it after the course. You know? You can learn it even during the course if you have time. You are not doing
Yes.
anything. Then basically the aim is to get you through the complete flow. The first step is very long, and that is why we insist that to some extent you should be able to understand the Verilog. That is why I have cancelled my plan to cover FSM today. We'll do it tomorrow, and then move with the things as we go in the class.
So, but most of the projects use FSM.
Right. So they use. So we'll have a very simple FSM. Today we
Okay.
saw a counter, a full adder. Okay, that will become two parts of our FSM, and
Okay.
I will have a control signal. Okay, so I just control both of them, and it will work fine. So it will not be very complex. So a very simple project we'll define. Okay, you can
Okay.
extend it to whatever you want, because the access of these tools will be provided till the 6th week of the program. Okay, so till the
Okay.
6th week ends, the access will be with you. So you can extend the project, even send it to Sneh, so he will be happy to respond, give you feedback. Okay, so all that you
Sure,
can
sir.
do.
Thank you, sir.
So
Okay.
there are two terms like Verilog and Verilog A. Are these two are these same languages or are different?
So actually, Verilog A is Verilog AMS, which is analog and mixed signal. You define functionality in the analog functionality in Verilog A. Okay. For digital design, only Verilog is used, which is synthesizable. Verilog A is not synthesizable language. You cannot derive a circuit out of Verilog A. Verilog A can only give you a behavior. Okay. So that is a complex topic. For now, we can focus on Verilog. Okay. Verilog A is not required in digital domain, although it is extensively used in analog and mixed signal verification. That is a different jargon
So
altogether.
in verification domain, isn't system Verilog preferred there because it is a hardware verification language?
Yes, so system Verilog is actually a derived form of Verilog and C++. Okay,
Okay.
so someone who knows how Verilog works will be the one who will be able to learn the system Verilog.
So
Without
is it a complex language?
system Verilog is basically you can't say it is complex if you understand OOPS concept, the
Okay.
object oriented programming, and then you understand the Verilog concept and the timing. So basically the Verilog stratified queue, all these things. So these are quite complex things. But if you understand all these things, it will be a matter of 1 week or 2 weeks that to understand these the system Verilog and other derived UVM and OVM, these languages. These are verification So verification guys use these languages.
So are they also easy to implement OVM and UVM?
See, UVM I have not learned. SV I know. Okay, so
Okay.
UVM I have heard from the seniors that it is quite difficult.
So my friend is in industry, so it's a bit complex.
Yes, so UVM is quite difficult. System Verilog is easy. It is not as difficult, but UVM in itself is a lot of effort. So you need not necessarily do verification only. So design jobs are there. You are so you can do circuit design, analog design, many things. But okay, once you move to industry, you will be able to learn these languages. But in the academia, it is not what is. So industry does not expect you to learn to know the UVM, OVM. Okay. They expect just the system Verilog, maybe sometimes system Verilog. Mostly only Verilog will do if you are aiming industry.
Okay.